people can join us if they come in. But so first I'll introduce myself. I'm Sepehr. I'm actually currently in third year studying physics, maths, and data. So I've done a bit of physics and maths. So hopefully I can give you some interesting insights that I've learned over the years. And in fact, some of my own research I've been doing kind of on the side. And what I've been really interested in is kind of, we learn a lot of quantum and stuff in high school and in fact in university, but what really is going on in a maths level is quite hidden under the rug. Usually you have to dive deep in order to actually understand this stuff. And so what I've done here is try to kind of package everything in a maths way, from a mathematical perspective, in what is actually going on in physics. So I'm going to assume you guys don't know anything about physics. I'm going to assume maybe you know like hydrogen and all that stuff. But from the mathematics perspective, I'll assume you know some linear algebra and calculus, so then we can actually get some interesting results out of this. So what I'll first be looking at is the idea of spin and how this is fundamentally connected to something called representation theory. This is something you might see later on if you go into honors mathematics and stuff. And then we'll actually connect this idea of spin, which I'll define, to something called topology. And if you don't know what this is, we'll also go into what this is. So the big idea is that this idea of spin, which is something you always hear physicists talk about, this random thing that seems to be very mysterious, is actually something that is related to the topology of the space we live in. In fact, if you live in three-dimensional space, it turns out that you can only have two types of particles. Let's say, if you know what these are called bosons and fermions. And these two types of particles can only have half integer or integer spin. But if you actually now go into higher dimensions, you get the same result. And if you look in two dimensions, something interesting happens. And you actually no longer have half integer or integer spins. You can actually have any rational number of spin. And I'll define what that means. In fact, this is where Microsoft recently, at the beginning of this year, has actually been looking into this, and these sort of particles that have this fractional spin are called anyons, and these are two-dimensional topological quasi-particles, so that's a bunch of jargon, and I'll define what that means, and this is used for quantum computing. So if you guys know anything about quantum computing, the basic idea is that you want to try to be able to do logic, but by using particles as being a way of capturing your state. So the cool thing about this situation, when it's topological, is that if this is pulled off by like Microsoft, they can actually use the topological nature of these anyons, and I'll go through this, in order to actually make more robust ways of doing computation. And the reason is, if you kind of imagine what topology means, and I'll go through that, it sort of weakens the notion of geometry, so you can allow things to have some wiggle room. So if your particles are getting jittered around in space because of noises and random error, this sort of thing, this topological property, actually allows you to be a little more robust, and it can allow you to do better computation with that. So let's go into beginning from the basics of physics into understanding this. So what we'll first do is understand where did this all come from? What is spin? What is physics doing? What is quantum? The simple thing that we can think about is just a single electron. So if you know what this is from chemistry, it's just a little thing of a little tiny particle that goes around and whizzes around in your body and everywhere else. If you shoot this, and you can think of this electron, these little balls, as being like little particles or little footballs, if you kick them through these two posts, you should expect that if they're particles, they should land on the back exactly following the trajectory they found, and you will get two bright spots at the back. But that's not what happens. In fact, if you send these particles one by one, you don't get that. You actually get something called this interference pattern, and that's where you actually get multiple bands of where these particles land. And this model, right, we need to be able to explain what's going on, what spin is doing, and all these other quantum phenomena. If you use waves, and if you thought about like two ponds, if you get a ball and just bob it into a pond, you would actually see these ripple effects coming out, and that's consistent with this idea of getting an interference at the end. But this is not happening for waves, this is happening for single electrons. And so the idea the only way to explain this is the electron had to be going through both slits at the same time and interfering with itself on the other side. And so that's the notion of where like quantization starts to come in, because de Broglie, which is one of the physicists, said that everything must be both a wave and a particle in order for this sort of thing to happen. The electron has to actually also be a wave. So in order to explain this mathematically, we need to come up with some model that can actually describe this sort of situation. And the trick is to actually use probability, and that's what Born and Schrödinger did. And they started with some ideas, so I'll try to give an analogy of where this all comes from. If you guys remember first year linear algebra, you might have done some Markov chains kind of at the end as applications. So if you imagine you got some state space, so this might be the number of light bulbs I've got on, like I could have 1, 2, 3 light bulbs, and I could have 1 on, I could have 2 on, or 3 on. That corresponds to a state of the system. Now, I can imagine this is my state space, and this is a particular time, right? This t is a particular state at a particular time. And in linear algebra, at least, you describe this as a matrix in order to get to the next time. So you times by some matrix that has a bunch of probability of transitions, and this allows you to go to the next time. But if we wanted to actually kind of do this iteratively, you can imagine going all the way back to the beginning time, whatever it was at the start, and just raise the parity. So really all the information is embedded in that state, for Markov chains at least. So what I'll do is write it as like a vector. So you've got 3 states, the probability of initially being in the first state, second state, and third state. And then I'll do some manipulations. So I'll write it like this. So this is written in the standard basis, like you've got your E1, E2, E3. And to make this quantum, we're going to just simply relabel all these into some physics notation. So what we do is replace this vector, which is vector as you saw, into a ket, and then we simply replace this EI into this ket notation to label the index, and then we've got the probability being replaced by some complex number. Now, this is where people are like, what the heck, where do complex numbers come from? Like, why are they in physics? So this comes down to the fact that when you have things like waves, which we saw, these are actually better to model with complex numbers because of one of the facts you might learn in Euler's identity, which is that rotations get turned into multiplication, and that's nice, especially for waves. So if you have this sort of thing, you have your constants being multiplied by your ket, and because we want these to be probabilities, we want the sum of these probabilities to equal 1. And that's equivalent to your inner product of this vector, so your complex inner product, so you're going to conjugate there, to be 1. So this is sort of what we got out of this. This is the quantum notation. You have a complex cube space with the inner product to be 1. But we can actually do a little bit more. We can actually imagine putting any like modulus 1 number in front of these constants, and they would again, because you have a squared amplitude, they would just disappear. So really, we want one more thing. We actually want to get rid of everything that is some sort of Bayes multiplier. So this is actually where you can generalize state space. And the idea behind this is you start with some set, and now you want to get rid of your zero vector and then simply associate every constant. So if you've got some vector, you want to associate everything that has a multiplier just by being the same vector. Because that's really what we were doing when we were assuming that the inner product is 1, and we're also going to now get rid of any phases. We associate them to be the same. So this space is actually called a complex projective space. So if any of you go down the line and study geometry, this is something you would actually see a lot in Riemannian geometry. This is quite an important space, but of course it shows up in quantum from the beginning. So the nice thing about this is we've got a projective space, and this thing, usually what we do is actually use a Hilbert space. So you can model particles in 3 dimensions with this special set, L2. You don't have to worry about this. All this is just some functions, such that if you take the integral, you get a finite number. And then the nice thing about this set, it's a vector space, and it also has an inner product. And the nice thing about that is you get this inner product, and if you want to be a physicist, you can write it as like this ket notation. That's really the same as having an inner product. So this is sort of the background of physics, but we're now going to use these ideas to actually get to something important. So we know that the idea of turning things into waves, turn them into probabilities. So really, if you've got something in this complex projective space,
you want the inner product to be 1 with itself, so you get this condition here to have the integral be 1, and then you can intuitively think of that as your electron, or whatever you're modeling, to be, if the particle is in this point in space, that's approximately whatever this square thing is times the volume element there. So these are some, if you don't know what these are SPDF orbitals that show kind of, as a function of where you are on a sphere, what the probability of you being there is. But we won't really go into this. But the idea is you can model particles just using these cats. So now we'll talk about spin. So that was kind of a background on quantum mechanics. Now we'll specifically focus on spin. So here I've simply got a hydrogen atom, so you've got a proton, and then an electron, and in the model you can just think of it as going around it. The big thing that comes out of spin is really angular momentum. So what is this thing? You start with your radial vector and cross product with your momentum vector. So it's spinning like this, for example, and if you remember your cross products, you get out some vector pointing out of the page, or up page here, and that L is the angular momentum. But the good thing about this is that it actually has some properties that we want to preserve in a second. So there's some nice things about this that comes down to spin. So we've got angular momentum. We've got the first time we actually saw spin, it was some experiment called the Stern-Gerlach experiment. They send a bunch of little atoms through, and if you send them through one by one, if you send silver atoms, they actually get deflected. Now silver atoms are neutral, so they shouldn't get deflected in this model, but they do. And the way we know they get deflected is that they must have some sort of magnetic property. And it turns out that this is because of the electrons on that atom, and they have some sort of magnetic property that attracts them to one of these magnets. And if you send it once, it'll either go up or it'll either go down. And the way we think of this is there was some sort of measurement being done by this experiment here. But that magnetism is exactly spin. So this is where physics gets a bit weird, because angular momentum is only defined when you have something rotating around something else. But spin, you're thinking about it as something rotating about itself, which is not really well defined, because in order to think about this, you would have to take some sort of limit as the radius approaches 0, which is not really, it's something a bit strange, but the way you model this magnetism is something that is really angular momentum at a limit where the radius of this rotation goes to 0. So what we're going to do is use this model of spin, which is really just something that's as fundamental as mass, right? It's just out there, we can use it, and we're going to model it like this. So in order to understand spin, we're going to have to take a route through some mathematics, through some group theory. So if you don't know group theory, I'll just give you a bit of an introduction. It's just really a set, and you've got some binary operation on it. So something simple is when you don't have you have the real numbers and you get rid of 0, you can do multiplication, and you can also want your group to have inversions allowed. So you want to be able to take your multiplication and undo that multiplication, which is really just division. But if we want it to be, more than just some multiplication, we can do something cool like Rubik's cubes. If you actually get a Rubik's cube, it turns out that because of group theory, if you come up with any algorithm, like randomly move one of the Rubik's cube parts around and just do this over and over, because of group theory, you actually have to land where you started. So that's one of the facts about that. But in this case, you've got something like always to change a Rubik's cube, and then your multiplication, I guess, is a composition of actions. So this idea of group theory we're going to actually use, and now think about what we want to do with this. This actually can encode symmetries into our problem. And in the case of angular momentum, we've got to think of what symmetries we want to actually encode, and the way we do that is by thinking about something like, if I've got my vector, what can I do with this? What can I do with the world around such that the vector is still in the same direction? And if you think about it a little bit, what we can do is really spin the whole world around that, right? So if I've got the vector like this, and I spin everything around it, then that vector will still point in the same direction. So in a way, this is a symmetry for this vector. And if you had another vector, you can rotate around that, and you get another symmetry. So if you have this sort of thing, this is a symmetry. So we want this symmetry to be imposed on this in order to be able to actually go down to getting a grasp on what spin really is. So this means we want the symmetry to be rotations. So let's go through to understand what rotations are. These are things that preserve orientation. You know that if you rotate something, you don't suddenly flip the whole world into a reverse image. So we want the rotation to be a matrix that preserves orientation. We also want it to not change lengths of vectors. So you want the length after the rotation to be the same as the original length. Now, I won't go through this too much, but you can show that the lengths, if you do a bit of algebra, it turns out that that's equivalent to saying that one R transpose R to be the identity. And then if you do determinant stuff, it turns out that if you want the determinant to be positive, it has to be 1. So this boils down what rotations are. It's matrices that satisfy these two properties. So what we're going to do is put that all into a single set, and that's where we get the special orthogonal group. So if you've studied any algebra, this is pretty important because it has some information in the way rotations work, but it also is pretty interesting on its own in Lie theory, and we'll go into that in a second. Now, it turns out that this is a topological group, and it's also a manifold. So how can we think of it as a manifold? The way we can think about it like that is by thinking about it as a set of solutions to an equation. So what we can do is start with some matrices in the set of matrices. So these are 3 by 3 matrices. So that's the same as kind of having a 9-dimensional space. You start with matrices, and then now you want to spit back out a matrix, and you want it to be M transpose M minus identity, and we really want this to be 0 in order for that to be a rotation. So if you've got the set equivalence, you might be getting confused here, so I'll just give you an example of what you might think about as a set of solutions. So one thing is x squared plus y squared minus z squared minus 1. That's the set of solutions to a sphere. So in this case, we've got something that's in 9-dimensional space. It's actually a 3-dimensional manifold embedded in 9-dimensional space, and it's really the set of solutions to a function. So it's a bit abstract, but you can think in analogy to a sphere. So what are we going to do with this thing? Well, remember, what we're trying to do is think about rotations. We want to find what gets preserved on the rotations. Those are spins, right? So we want to find some space such that they are preserved under rotations. So if you take a rotation out of this and then act on this space, you get back the space. That's kind of what we want to do. So what we'll do is think about being in this space somehow, so we can actually parameterize it. So if you think about to a sphere, you can use something like spherical coordinates. You can move around on your sphere using spherical coordinates, theta and phi. This is like latitude and longitude when you look at Google Maps, right? So if you have this sort of thing, but you apply it on the manifold, you've got some sort of parameterization, so you can move around in your manifold. And once we do that, we can actually imagine it as being some sort of cross-section. We can take some cross-section through this 9-dimensional space and imagine this manifold. So these red points all correspond to being inside our manifold that we're interested in. So remember, it's a group, but it's also a manifold, so it's got a lot of properties. And what we're going to be looking at here is the tangent space. And why do we look at the tangent space? So what does that mean? If you remember calculus, it's really, you get the tangent vector at a point, and if you're in higher dimensions, you can kind of do similar things to get a tangent vector. And if you think kind of intuitively for a second, we want rotations to preserve something, right? So we want to do a rotation and then get back the same thing. So it turns out, if you look in the tangent space, if you think about it for a second, if you kind of move around a little bit, if your rotation moves around, you want this point here will kind of stay in the same point. And in fact, it turns out you can do a very specific thing. If you've got some vector here and you want to figure out what preserves it, you can go forward in a very specific way and find some rotation matrix. So this rotation somewhere here, and this would exactly be what would preserve this under a rotation. That rotation would preserve that. And conversely, you can actually start with any vector in this tangent space and go back to the tangent space around the identity, which is what that one is there. So what the summary is here is everything we need about spin is actually going to be encoded in this single tangent space. And that's where we get something like this. We get the SO3, this little SO notation is exactly the tangent space and the identity of this manifold that's also a group. this here is a set of solutions to our problem. And this here is where all our spins are going to live, because these are the things that actually get preserved under rotations. And these things here, you might not know what this is, but this is actually a Lie algebra of this set, and it's where our spins are going to live. So what does this Lie algebra business do? Well, first, if we look at the special orthogonal group, physicists like complex numbers. Here we don't have any complex numbers, it's just rotations in real numbers. Physicists, it turns out that if you look at the SU2, which is the special unitary group, you can actually show that if you get the Lie algebra for this, that they're actually isomorphic. Remember, these are vector spaces because they're like tangent to a manifold, so they're actually vector spaces. So isomorphism makes sense in this context. And these two are isomorphic, so physicists actually work with this instead. So you can actually come up with a basis for this set. And if you do any physics, you might actually recognize these things. These things are exactly the spin Pauli matrices that you're always using, but when it was introduced, there was no like sign of where it came from. So these things here, if I call that sigma x and that sigma y and that sigma z, these things are a basis for SU2. You could have used another basis, but this is one. Now, it turns out that actually, if you use, let's say, a bigger matrix, you could have actually chosen like a 5 by 5, or even a bigger matrix for this set. And you could have actually had the whole thing still span to give you the same set, but using a different representation. So if we look at that, that actually will be pretty important in a second, because this will be one of the big theorems that tell us that we only have fermions and bosons. But in the case of when we have sigma x, sigma y, and sigma z, here, because this is a Lie algebra, it emits something called a Lie bracket. So because these are matrices, you can just literally think about it as being AB minus BA, that's a commutator. Turns out they've got some special relation between these, and these actually put a restriction on the eigenvalues of these matrices. And the restriction turns out to be exactly what corresponds to spin. So no matter the representation we use, so I could have used a massive matrix, so this could have been a 9 by 9 or something instead of just a 2 by 2. And no matter what matrix you use, it turns out the representations will always give this non-abelian Lie algebra, and the Lie bracket will always satisfy this property. And this actually will put a bound on what our eigenvalues have to be. And in fact, it turns out that the eigenvalues of these matrices have to be multiples or half multiples, so half integer multiples of some constant. So this comes out of representation theory, nothing to do with physics so far, but this is exactly what's going to be used in physics in order to give us some understanding of measurements, because in physics at least, they view the eigenvalues as what would happen if you start with your little space of eigenvectors of these spin matrices. You view these eigenvalues as being what would happen under a measurement of that operator. So in this case, you can view these as operators. So these eigenvalues, in this case, would be a half, and if you did other representations, they would be like multiples of some number, or half integers in this case. So now we're going to connect this notion that seemed very random to something in topology. So first we need to understand topology. So this is that derivation we saw as predicting that we get half integer or integer spins. Now, what do we actually think about this in the real world? Like, do we actually think that these random matrices actually represent anything in the real world? Well, there's actually something that will help us understand that, and we need to understand topology in order to get to that point. So if you don't know what topology is, it's the notion, as I said, you can allow things to wiggle a little bit. So in this case, I've got a little coffee cup and donut. So you can imagine a donut being continuously deformed into a coffee cup. And if this is the case, you can do this, you can view these as being topologically equivalent. So this notion of allowing a little bit of wiggle room is what we'll have to think about when we go to something else called the spin statistics theorem. So this theorem actually creates a connection between our model of spin, which seems pretty random, and this actually connects into the real behavior of particles. So this is something that comes out of physics, and we're going to just use it here. And the way we can understand this and what the statistics actually are, it has to do with exchanging particles. So if you think about it, when we see these walls here, really they're made up of particles, but to us, when we look at these walls, they're actually quite identical, except some defects and stuff. If you ignore the errors in like the way the walls have been built, really you can't really tell apart any particle in the space. And these actually correspond to the statistics, because in the case of fermions, they're particles that you can't put in the same location at the same time, but bosons you're allowed to do that, and that comes down to these cats. And the way we're going to understand that is by thinking about these two identical Hilbert spaces. There's a notion of a product, it's some tensor product, we won't go into that, it's just the only reasonable way to take a product of vector spaces, and you can write some ket in this space, or vector in this space, as being some sort of thing for particle 1 and particle 2, and then we look at it in the projective version of this space. And once we have that, we can imagine visualizing the particles in three dimensions, and now I've got these two particles there, but as I said, we couldn't tell them apart. I've only put an index there, but that index is not there in the real world. You couldn't tell them apart. So if I swap the two, now I've got particle 2 there, particle 1, to us, this is exactly the same system. So in the way we view this in quantum mechanics is if you swap the indices, that's something that corresponds to the same system up to some phase. And that phase, remember, doesn't actually show up because we're in projective space. We view this phase as being some sort of equivalence relation, so we don't actually see that phase in the real world. And that phase there is something we're going to have to figure out if we're going to understand this. And it turns out to actually connect that phase into something real, there's something it has to actually do with the winding angle of this particle as you move around the other one. So this is where the topology is starting to come in. This has to do with some very complicated stuff that's done later on in physics. But it turns out that if you've got a particle, and if you want to move it all the way to the other side, while you're going there, whatever the winding angle was, is going to actually be exactly corresponding to the exponent you get. So if you actually did some wiggle room, like I've got a pretty circular path here, you don't have to have that. You can have some weird path, as long as you end at the same point, whatever the winding angle was is exactly going to correspond to the phase you pick up. Now, if you imagine, we can just keep doing this all the way to the end, right? And what would happen if I put the particle all the way at the end? I could just imagine I would have the exact same scenario as before, where the particles have gone over here, but we just move them over here, and that wouldn't actually correspond to any changes. It's still the same system because we're viewing three-dimensional space as being isolated in this case. So if we put it all the other side and just move them both, that means we actually can figure out exactly what that theta is. And that theta, if you do that, you can see you get this exponent, and once you go to the back, we get this theta, and we'll, before we do the equality that I was mentioning earlier, we will have to use something called spin statistics, and this is some theorem from physics, which says that if your space is Lorentz invariant and causality holds, that's some space-time theory stuff, we don't have to worry about that. What it does tell us is that as long as you've got this situation, this exponent you get out, or this number, it's going to be -1 and 1 in this set, if and only if the two particles you started with have half integer or integer spin. So now it's connecting this random topological property back to spin, which is something quite weird, right? So this is spin statistics, and it's quite hardcore to get to this theorem, so I'm only going to give you the fact right now. So going back to what I was doing, we can go all the way around and imagine moving them back, so it's kind of like we get exactly what the phase is. Once we have this phase, we can actually now continuously imagine getting that plane and rotating it like this and apply exactly the same argument. I simply, relative to P1, I simply move my particle up there, do this phase calculation, and I get exactly the same thing. Now, you can imagine I continuously do this deformation, take it to the other side. Now I've got back to the same plane, but now on the bottom. But I can also do the calculation another way. I can actually go backwards when I'm starting over here, I can go the other way, do this calculation. Now I've got these two phases, and these two results must be equal. And so that actually tells us we have this property that the 2 pi I nu is equal to 1. So if you do a bit of algebra now, you can show that this nu, which is our statistic, belongs to the set 0, 1, or 2, which actually tells us that this thing here is actually -1 and 1. So what happened is, because this sort of winding angle is a thing that's really only defined in 2 dimensions. It only really makes sense in 2 dimensions. We were actually able to continuously deform it to get some sort of bound on what the numbers have to be. And if we apply the spin statistics theorem, that tells us that we must have half integer and all integer spins in n equal to 3 dimensions, which is what I did, but in higher dimensions, just apply the same arguments, but you would have some abstract space. Now, we'll see this property actually breaks down in 2 dimensions, and that's really because if you imagine a plane like this argument I just made about moving the plane is going to not work anymore if you're in 2-dimensional space. You're not allowed to move in this high dimension in order to move your particles around. And so these particles, when they're trapped in 2 dimensions, there is no bound you can come up with on what the eigenvalues have to be. So this actually means that we get something else. We get something like the spin statistics theorem breaking down in 2-dimensional topological spaces. And if we go back to spin representations, if you look at SO2, which is now rotation matrices in 2 dimensions, if you actually look at the group, it's actually an abelian group, which means you can swap it's a commutative group. You can swap the elements and you still get the same result, which means this Lie algebra is also abelian, so this commutation relation is 0. And so this actually means you can't put the bound on the eigenvalues anymore. And so in the case of quantum mechanics, you can actually get any rational eigenvalue. And this is where we get the fractional spectrum for spin states. So this notion of a topological property came out because of this winding angle not being well defined in n greater than 3 dimensions. So this is where we start to actually see it being used in the real world. And then if you want to understand how to actually turn this into quantum mechanics like computation, you can use the fact that we have particles, if they're trapped in 2-dimensional space, you get fractional spins, as we just saw. Now, if you imagine space-time, which is some sort of 4-dimensional manifold, but in this case we've got some cross-section. If you imagine this as being the time axis, and this as being, let's say, x and y, as you move up in time, your particles may move in different locations, and the phase you pick up is exactly going to be, they're going to exactly look the same at the top, but the phases you get out are corresponding to the knots you created in space-time. And studying these things through braid groups and hopefully polynomials is exactly what is required if you want to use these to do computation. So this is where you can do really crazy stuff with this. For example, with Microsoft, when they were trying to actually use these fractional particles in 2 dimensions to do computation. So that's where we go from nothing in physics to kind of understanding a little bit of physics. And yeah, that's the talk. I hope you've enjoyed. Any questions? You want to give me? There you go. So spin is a topological property. There you go.
Why are the eigenvalues only rational?
So it's a bit of effort to get to that point, but when you have that, when you have this Lie algebra bracket, you can do an argument regarding the highest and lowest eigenvalue. You can do an argument to say that there exists a largest and lowest eigenvalue, and then it turns out that you can split those eigenvalues up in a very specific way because of this Lie algebra bracket, and once you do this splitting up, there must be multiples of some number, and this number you could show as half multiples or integer multiples. So it's really coming from this Lie bracket that you can get that property. So I won't go into it fully. It's a bit of algebra. You have to do a bunch of work to get that. But does that answer your question? Or?
Oh, I was thinking about when it's 2-dimensional. So you don't have any.
2-dimensional when you have now. Now it's an abelian group. So you get this 0 thing. So the bound is no longer possible in that way. So you can actually get any spin. In this case, in the real world, you get rational spin, which is only what we're able to actually do with these. But in a limit, I guess, because if you wanted to do very, very massive windings, you could get real eigenvalues. But in the real world, we can't really do that. But yeah, that's the reason why in 2 dimensions it doesn't work. You get any fractional spin. Okay, anyone else?
So they managed to actually do that and make it work?
Yes, so there's something called the fractional quantum Hall effect. This is physics now. They trap particles using very special techniques that it's to do with very, very precise equipment that does trapping with the magnetic fields. So you can trap particles to just live in 2 dimensions. And by doing that, they behave as if they have fractional spin. So the statistics, which is like the boson and fermion stuff, the statistics in that case is you can't put 2 fermions in the same location. In this case, you get very weird results where you can put these things around each other, and that is something that you can actually measure later. So this is how they can store these quantum states using these winding around each other property. So yeah, it's a very specific physics experiment. There's a fractional quantum Hall effect if you want to look it up. They've actually trapped these particles into 2-dimensional space, and then they were able to do this sort of thing. Yeah, any other questions?